Hello, everybody. I'm doing this recording a little bit different than other times when I've done it from home. I wanted to be able to point out things a little more easily and also use my hands to demonstrate some things as we have some somewhat difficult concepts to get to a little later in this lecture. So, hello. Thank you for your patience with my missing another class yesterday. I'm sorry about that. I really hate to have to do that again. Feeling much better today, but the last 2 days I didn't feel terribly great. So thank you for your patience with that. I believe if I am to finish up to chapter 10 in this particular video, we're not going to do a whole lot with chapter 11, and there's really just one concept in chapter 12 I want to do, so we can finish those up in Tuesday's class and then have a review on Thursday. So this is going to finish up chapter 10, and you'll need it to be able to do chapter 12 once we get there. So this is where we left off last time, talking about this idea of rolling motion, where we have both a combination of rotational and translational or linear motion. The object is moving from one place to another, but as it does that, it is also rotating. We're going to be looking at a very particular type, which is rolling without slipping. This is the case where it's somewhat like walking. In the case of walking, I put my foot on the ground, my heel touches, and then I roll my foot forward as I take the step. But at no point is my foot dragging along the ground. It's not slipping. Also, if you think about a bicycle tire rolling, it is rolling without slipping if it's working properly. A little piece of the bicycle wheel touches the ground, and then it rolls forward, but the bottom of the wheel doesn't slide relative to the ground. This is the only type of problem we're going to deal with in this particular class. And it turns out that if we have rolling without slipping, then that point at the top is true. And that is that the translational speed of the object, how fast the object is actually moving forward, is equal to the tangential speed of a point on the edge of the object. So if we look at a wheel, and let's put that wheel on the ground. Whoops, it's floating. It's still floating, but you get the idea. And let's say that it's rolling this way with an angular velocity omega. Well, then we could look at the center of mass of the wheel and say that it has a velocity moving this way as well. And you can see that those two velocities, the angular velocity and the regular velocity, are intertwined. As this rolls forward just a little bit, with each little piece of rolling motion, you get a corresponding linear motion that corresponds to the arc length that touches the ground. And it turns out that as long as we're rolling without slipping, we can make this connection and look at the tangential speed of a point. So V tangential, which we remember is equal to R times omega, will be true in this particular case, and it's also equal to how fast the wheel is actually translating forward. So we'll be able to use that expression, V is equal to R omega. Vt is equal to R omega is equal to V, as long as we have rolling without slipping. So in this particular case, we have a rolling object that has regular linear kinetic energy, 1/2 mv squared, but also rotational kinetic energy. And I can get the equation for that particular type of kinetic energy rotational, by just looking at the exact same equation and rewriting it in terms of angular expression. So remember, we now know that mass in angular terminology is moment of inertia, and velocity is angular velocity. So these are our corresponding angular expressions, which gives us a corresponding rotational version of kinetic energy. So the rolling object is going to have both of these types of kinetic energy. So we can do conservation of energy and include rolling motion. And the best way for me to do this is just to go to the next slide and do an example. And you can see this time we have a solid sphere, and it's going to be placed at the top of an incline. It's released from rest, and it rolls down the incline without slipping. It wants us to find how fast the sphere is moving when it reaches the bottom. Not how fast is it rotating, but how fast is it actually moving forward. So let's pretend we have an incline that looks something like this, and it reaches ground level. What all do they tell us? Let's say that ground level is y equals 0. Our sphere is here at the top, and it is at rest. And let's see, they told us the height of this incline is 0.12 meters, and it has a length of 3.5 meters. So, of course, none of this is to scale. We're going to say here at rest is the initial position, right at the bottom is the final position, and we're going to use conservation of energy. So kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final minus WNC. If it's not moving in any way, rotating or moving forward at the top, then that kinetic energy is 0, but it does have potential energy equal to m times g times y initial. Once it reaches the bottom, it's both moving forward and rotating. So it has two types of kinetic energy, 1/2 mv final squared plus 1/2 I omega final squared. The potential energy is now 0 because it's reached the bottom of the incline. And this may be a bit of a sticking point for people, but we're also going to say that the work done by non-conservative forces is 0. And here is the reason why. First of all, we can say that to roll without slipping, friction must be present. Otherwise, it wouldn't roll at all. It would just slide down the incline. Okay, there's no way for me to walk if there's no friction. My feet will just simply slide and they won't roll forward as I walk. So friction must be present. However, this type of friction is not about an object that's sliding against another object. So it's not the type of friction that we know about. This type of friction is something that's known as rolling friction. And it is much less than the other types that we know about. Much, much less. It's so much less that we are going to assume that it is negligible in all of these types of problems, which is why I can set that work by non-conservative forces, or work by rolling friction in this case, equal to 0. So there is friction, it's just really small, okay? So now we want to find V final, but don't forget that omega final has a V final sort of tied up inside it as well. So a couple of different asides here. First of all, omega final is equal to V final over R. We're going to make that substitution. And also I for a solid sphere. You can go back and look that up on the table a few slides back. I for a solid sphere is equal to 2/5 mr squared. So we're going to make both of those substitutions and see where it gets us. So plugging those in, we now have mg y initial plus 1/2, equals 1/2 mv final squared plus 1/2 times 2/5 mr squared. And then omega final squared, which means I'm going to have V final squared over R squared. Okay, and then we have everything plugged in, and we can see where this gets us. So some things are going to cancel out. First of all, I have a mass everywhere, so that's gone. These R squareds cancel out. These 2's cancel out. And now I have gy initial equals 1/2 V final squared plus 1/5 V final squared. Nice. So if you get a common denominator, the 1/2 and the 1/5, add those and you get 7/10 V final squared. And that's equal to gy initial. And we're solving for V final. So that's going to be V final is the square root of 10/7 gy initial. And we have all of those values. So V final, let's see if we plug those numbers in. 10/7 times 9.8 times 0.12 should give you 1.3 meters per second at the bottom of the incline. So you could do this the other way around too, and maybe try to find omega instead. So maybe you want to find how fast is it rotating at the bottom? Well, if that's the case, then use this equation to substitute in over here so you get both terms in terms of omega. And then you could find omega final instead. Or once we have this, V final, we could just plug it in here, divide by the radius, and find out how fast it's rotating as well. So that's another option. Okay. So that is rolling without slipping. That's an example of kinetic energy rotational and kinetic energy translational in the same problem, which brings us to something that's new, and this will connect to chapter 12 as well. If you think through the things that we've learned about so far, we are stepping through rotational and angular versions of all the same quantities. The last one that we did was kinetic energy. Before that, we did mass, and we found a rotational version of kinetic energy. We found a rotational version of mass. What we need now is a rotational version of force. So you might remember we asked ourselves what was making things move way back in an earlier chapter. Why are things accelerating? And we said forces. Forces make things accelerate. So now we're going to ask ourselves the question, why is anything rotating? What makes an object rotate? And the answer to that question is something known as torque. So a torque is analogous to a force, but it is not the same thing. A torque occurs when a force results in an object rotating, when a torque causes a rotation. So first of all, we're going to use tau, the Greek letter tau, to represent torque. And this may be a different equation than if you've seen this before, what you have seen before for finding the torque. We're going to do it maybe a little differently. You can do it the other way as well. It's totally fine. But what we're going to use is we're going to say that it's equal to the force that's causing the rotation times a term known as R sub perp. R sub perp. This R perp is known as the moment arm. Yeah, that's a little weird. And it is the perpendicular distance from the force to the axis of rotation. The perpendicular distance from the force to the axis of rotation, and I will show you what I mean. Before we do that, the unit here is just the units of those two things multiplied by each other. So force is in newtons, and R, a distance, is in meters, so our unit is Newton meters. And I will give you the alternate equation for this. So we'll say also, or torque is equal to R times F tan, which is the tangential force. We're not going to do problems using that terminology, but in case you've seen it that way before, it's totally fine. Use the exact same equations. It's just another way of thinking about it. Okay? So going back to this torque idea, let's say, for example, we have a wheel. So once again, I need a circle. There we go. Let's say that it's rotating about this axis right here in the middle. So that's the axis of rotation. And let's say we decide to spin the wheel counterclockwise. So let's say I apply a force right here. So there's my force. If that's the force, and you can see the axis of rotation, a perpendicular distance from the force to the axis of rotation is simply going to be this line, which is just the radius of my wheel. So this is R perp in this problem because it's perpendicular to the force. So there's nothing complicated there. In fact, you might be thinking, well, that seems like a great way to spin a wheel. That's where I might apply a force if I want to make it turn around counterclockwise. But what happens if we change things a little bit? Maybe instead of applying the force like that, we decide to, again, let's put the axis here. Let's apply a force at this point, but sort of pull on it out this direction. And if you're thinking, well, why would you ever do that? Imagine maybe this is like a part, like deep down inside of an engine, and it's a bolt and you're trying to unscrew it and you can barely reach it, and this is just the best you can do for applying a force to that bolt. It's not great, but maybe eventually you can get it turned counterclockwise and unscrew the bolt. Well, you know it's not great just by looking at it, and you know that because you're not going to get as much torque in this situation to help you unscrew the bolt. Here's the reason why. Well, the force is easy enough to see. It's just F, but if I want to find R perp, the moment arm, I need a line from the axis of rotation that's perpendicular to that force, and you can see none of those are perpendicular. So the way we do this is extend the line along which this force is acting out in both directions. So there's a line along which the force acts, and to that line we can find a line from the axis of rotation that's perpendicular, and it lives right here. So in this particular case, that is our perp. Notice it's less than the radius. Same force, less our perp gives me less torque, okay? So there are ways we could find that. I'll show you how to do that in a later problem, but I want to imagine sort of an extreme case. What if we do this again, put the axis of rotation there, and this time apply a force straight this direction? You might be thinking, well, sure, you're pulling on the thing, but you're not going to turn it by applying that force. You can't turn it because you're not applying a torque. And here's why. If I were to extend this force out, notice it passes directly through the axis of rotation. If it passes directly through the axis of rotation, there is no r perp. R perp is equal to 0 in this case, which means the torque is equal to 0. So here we have max torque. This is less torque. And then finally, 0 torque. Okay? Torque is when a force causes a rotation. Let me point out that torque is a vector, and there's a lot on this diagram. Don't let it worry you too awful much. Let me just point out that you can use that first of all, you can say that positive torque is when it is trying to cause a counterclockwise rotation. Negative torque for clockwise. And it may not even cause the rotation. If it's just trying to cause the rotation, that's good enough to call it positive or negative. But if we want to talk about the torque vector direction, we have to use the right-hand rule. Yay! Right-hand rule. And to use the right-hand rule, the way that you're going to do this is, first of all, we will say point your fingers, and you don't need to know a lot about this semester. You're going to use it a little more in 230, in the direction of R from the axis of rotation out toward R. So in this particular case, I'm going to start here, and I'm going to point my fingers in the direction of R. Now from there, you can see the force at the top. Notice it's pointing sort of off this direction from R, okay? It's not pointing along the same direction, it's pointing over toward that side. The other option would be for it to be pointing over toward this side. So what I want to do is orient my hand, once I've got my fingers pointing toward R, either this way or this way. But I want to flip my hand in such a direction that the fingers curl toward the side of the force. So I want to orient my hand this way because since I know the force is over to the left, I want my fingers to be able to naturally turn that way. Okay? When I do that, you can see my thumb naturally points a certain direction. It's pointing out of the screen. Out of the screen is the direction of the torque vector. So torque vector direction is the way your thumb is pointing. Okay? So R, F, thumb is this way, so you can see the torque vector points that way. Don't let that stress you out too much at this point. Again, using the right-hand rule will be something that's more important in 230. I just want to point it out now. So let's see, this is a little bit more about the vector nature of torque. It's the exact same thing as what I just told you, so if you want to use some of this to help explain what's over there, that's great. Some questions. You are using a wrench to loosen a rusty nut. Which arrangement will be most effective in loosening the nut? Most effective would be which one is going to give you the most torque. So looking at our options, notice F is the same for all of these. Force is the same. So which one has the longest R perp? So in this case, R perp is this line. In this case, R perp is still that line. So R perp is the same for 1 and 4. In this case, this whole distance is the perpendicular distance between the axis of rotation and the force. And again, the axis of rotation is the nut. Okay. And this one is a little different. Trying to draw the perpendicular line is a little hard, so this is the perpendicular line that goes over to the line that's being formed by the force. So it turns out that this one has the largest R perp. So therefore, this one has the most torque. Okay. Next one, two forces produce the same torque. Does it follow that the forces have the same magnitude? Well, no, because our perp could be different. I don't know what that word was. Two forces produce the same torque, so our perp could be different. Okay. And finally, which one of these gives us the torque the largest? Well, let's see. My axis of rotation is here, and we're kind of looking top down on a door. Which one of these is going to give me the largest R perp is the question. Well, you can see for force 1, this is going to be R perp. For force 4, R perp equals 0 because it goes straight through the axis of rotation. And then for force 3, to draw a perpendicular line, I have to do something like this. Then R perp is going to be here for force 3. Well, the one that has the largest R perp is force 1, so it's going to give us the most torque. So R perp largest. Right? So let's work an example and see how some of this comes together. So notice it's a nice blank screen, and let me just scroll ahead to see what else is out here. Okay, good. So there's a lot of the stuff that we're not going to be using or needing or doing. So it turns out that we need to do this example, and then I'm going to point out something about Newton's second law again, and then we're going to use torque more in chapter 12 when I'm back in class with you to help get these concepts across. Okay, so here is the example we're going to do. Let's say that we have a meter stick. Let's say we have a meter stick, and the mass of the meter stick is 200 grams, so 0.2 kilograms. Let's say that it is a uniform meter stick, so that means right in the middle should be where its center of mass is. And let's say that we're going to try to hang it on the wall. And keep it horizontal. Try to put it on the wall and keep it horizontal. So maybe one of you decides to take the meter stick home and do something that sort of looks like this. So here's the meter stick. And let's put some markings on here. Let's say 20, 40, 60, 80. So this would be 0, 20, 40, 60, 80, 100. Those are the centimeter markings on the meter stick. And let's say for whatever reason, right at the 30 centimeter mark, you decide to put a nail right here. And let's say the nail isn't tight enough that it can actually hold the meter stick against the wall in this configuration. But we all know that if you put the nail there, it's like, well, there's more of the meter stick over here. So it's going to try to like rotate like this, and it's going to end up vertical instead of horizontal. Well, that's not what you're going for, okay? So it turns out that you're like, well, clearly I didn't learn anything in physics class, so I'm going to need some help from friends. So 3 of your friends decide to come over and apply some other forces to help out. So one of your friends comes to the 80 centimeter mark and applies a force directly this way to try to keep it horizontal. We're going to call that F1. And we're going to say another one of your friends decides, no, too much force there. That's not going to work. And they decide to go over to the 10 centimeter mark and apply a force this direction. We'll call that F2. So that's at the 10 centimeter mark. And then you've got a friend who's just causing problems and decides to go to the 60 centimeter mark and apply a force ridiculously off this direction. Yes, not terribly helpful. And we're going to say that this angle is theta 3. So let me give you some of these values. We're going to say that F1 is 105 newtons, F2 is 35 newtons, and F3 is 126 newtons. Theta 3 is 35 degrees. Okay? So you can see that we've already drawn sort of a free body diagram in the sense that we've drawn the forces that are acting on the meter stick. Notice they're not all coming out of the same point because this is the first case of using what we might call an extended free body diagram. We are recognizing that the object is not at a point and it has size, it has shape, it has dimensions, it can rotate, and forces can be applied to the object at different points on the object. So it's still a free body diagram, but it's all spread out. We draw the forces where they're actually acting on the object. The thing is, we're missing one force, and that is the fact that the meter stick itself has weight. And its weight is centered at its center of mass, which would be at the 50 centimeter mark, and it has weight that points straight down. So that's going to be the mass of the meter stick times g. And since we have the mass of the meter stick, we know exactly what that force is. That's the force that would make it rotate. If I just tried to put a nail at 30 centimeters mark, it's going to turn it around clockwise until it's vertical. Okay? So here's what we're going to find. We are going to try to find a few different things. We're going to find the sum of all the torque and the sum of the forces in the x direction and the sum of the forces in the y direction. Okay? Now you may be looking at this and thinking, okay, but are there any other forces? What about the nail? What's it doing? You're right. It's doing something. So I don't really know for sure at this point if the nail is holding it up by applying a force this way, or because there's so much of these other forces pushing up, maybe it's holding it down. But you're right that there is a vertical force from the nail here. But also you'll notice we're pulling on this thing sideways some, but it's not moving that way, which means the nail must be also applying a horizontal force to keep it from moving sideways. Okay? So right now I'm just going to leave this out. I just want to show you what could happen, and let's use the four forces that we have, and I'm going to revisit the nail because something is clearly happening there. So let's start with the torque. So the sum of the torque is going to be equal to torque from all four of these forces. So let's see. We're going to say that the torque is positive if it may cause a clockwise or counterclockwise rotation. So force 1 wants to make it rotate that way. That's counterclockwise. That's a positive torque. So we're going to start by saying positive torque from force 1. Force 2 makes it want to rotate the other way, which is clockwise. So that's going to be a negative torque, so minus torque 2. Force 3 also makes it want to rotate in the clockwise direction, as does the force from the meter stick itself. So those are both negative. So we're going to say negative torque 3 and negative torque from the meter stick. Okay? And we're just trying to find what these all add up to. We don't know anything about the right side of that equation yet. All right? So let's see. Each one of these is force times R perp. So we've got some numbers here. So I'm going to call the R perps R1, R2, R3, and R meter stick just to keep things simple. So this one is going to be force 1, R1. This one will be force 2, R2. R2, D2? I don't know. And this one is force 3, R3. And this one is going to be the force, which is the mass of the meter stick, G, times R for the meter stick. Okay? So the three forces and the mass and G we know. Finding these R's are the problem. Okay, so we need to go back to the diagram, and let's start with force 1. So my axis of rotation here, I need to draw a line that's perpendicular to the force from that axis of rotation. So that's going to be R1. So I can just look at that and see that it goes from the 30 centimeter mark over to the 80 centimeter mark, which is 50 centimeters. So R1 is 50 centimeters, which is 0.5 meters. Okay, so that length from here to here, from 30 over to 80, gives me a perpendicular line to the force 1, so that's not really a problem. Force 2, well, it's the same kind of idea. We can go from the axis of rotation over to the force. It's perpendicular. You can see that we're going from the 10 to the 30 centimeter mark, so R2 is 20 centimeters, which is 0.2 meters. So that one is R2. Let's see. Let's do the one for the meter stick itself. So we could say, and I need some color here, from the axis of rotation over to that force, goes from 30 to the 50 centimeter mark. So that one is our meter stick. So our meter stick is just 20 centimeters as well. So that's 0.2 meters. And then finally, it's this last one, this force 3. I need to extend it out in both directions. If you don't easily see a line or a distance that's perpendicular to the force from the axis of rotation, then extend the force out. And then you can find a line, and here our perpendicular line is right there. So this is going to be R3. And we have to do a little bit of trig to figure that out. So let's see. Theta 3 will also be this angle. And essentially, I'm solving a triangle that involves this segment. So I've got a leg here, this leg, and the hypotenuse is from the 30 to 60 centimeter mark. So that means we can say that the sine of theta 3 is going to be R3 over 0.3, 30 centimeters. And theta 3 is 35 degrees, so R3 is going to come out to be 0.172 meters. And now we have everything we need to go back to this equation and see what it gives us. So let's see, we've got 105 times R1, which was 0.5, minus 35 times R2, which is 0.2, minus 126, which is 0.172, minus 0.2 times 9.8 times 0.2. And you can add all of that up and see what you get. I've got, let's see, which sign convention did we use here? I believe it's going to come out to be positive 23.4 Newton meters. Notice the positive indicates clockwise rotation. So at this instant, if we just went up here and just, boom, applied all these forces, it would begin to rotate clockwise. And then, of course, the force directions and all change and everything gets crazy. But at that instant, it rotates clockwise. Now, let's go back, and we can do the same thing as before and just say to the right is the positive x direction, and let's say up is the positive y direction. And even though the forces are all spread out, we can still use the sum of the forces horizontally and the sum of the forces vertically and see what we get. So let's go right down here somewhere. The sum of the forces in the x direction. And the only thing in the x direction is a component of force 3. So F3 cosine theta 3 is the only force that we have there. F3 cosine theta 3. Which gives you something like 103 newtons in the positive direction. So that's how much pulling we have going this direction. And if it's not moving, then the nail must be applying a force the opposite direction that's equal to that. So that means the nail, so let's say nail sub x equals minus 103 newtons. Okay? And we can say that there must be this other force in the opposite direction because there's no motion. The sum of the forces in the x direction have to give me 0. So that tells me that there must be a force that's there. In the y direction, I've got this force up, this force up, this force down, a component of this force down. So in the y direction, we can say we have F1 plus F2 minus mass of the meter stick g minus F3 sine theta 3. And if you plug all those numbers in, you get 67.7 newtons. That's the net force up, but it's not moving up, so there must be a force from the nail that's equal and in the opposite direction that's holding it down. So we could say that the nail force in the y direction must be negative 67.7 newtons. Okay? And we could have made assumptions back at the start and said, ooh, the nail is applying a force. I bet it has an x and a y component, and I could have put it into these equations and just directly solved for it, and we would have got those two values, negative 103 and negative 67.7. So that is that example. Pour over this. We're going to be doing a lot more with torque in chapter 12. This is just kind of the start of it, but the rest of it we'll do on Tuesday, which leaves me with one slide I'd like to do in this particular lecture, and this is about Newton's second law again. So we previously learned that force causes acceleration. We learned that as F equals ma. That's Newton's second law that we learned before. But also we now know that torque must do something, and I bet it causes angular acceleration. Notice these things line up. We have the angular version of force, the angular version of acceleration. So it makes sense that I'd be able to write a new Newton's second law just using our counterparts in the rotational world. So force becomes torque, and acceleration becomes angular acceleration. And we know that mass switches over to I, the moment of inertia. So this is Newton's second law for rotational motion. We are not going to do a whole lot with that. I just want to point out that it's another analog in the rotational world. Torque is equal to I times alpha, corresponds to F equals ma from before. So that is the end of this video. Let me know if you have questions, and thank you for watching. Bye.